In this video, I would like to explain a bitmap compression technique that is widely used in practice. And there are also a number of improvements of this method, but I would like to explain the basic idea of this method. So let's go back to our initial situation where we had a relation colleagues and we have a bitmap on the city attribute. So that is displayed here. So for every value that exists here, you create a bit list here. So I here have a number of bit lists, and which means in the worst case, I have D different bit lists. D is a cardinality. This is a cardinality, so the number of different values I get here. And I have n tuples. That's visualized here with those dots. N tuples exist in the table, and therefore I have n different bits for each of the bit lists. So basically this means that I need to represent D times n different bits. And that is something I want to compress in the following. In order to explain this, I will concentrate on one bit list only. Of course, you will apply the compression algorithm also on the other bit lists, but in the following I will concentrate on this bit list. Let's focus on this one. And so I put this bit list up here. I rotate by 90 degrees, so it's still the same bit list representing the tuples that have that value 88 in attribute city. Some more data, some more bits. Of course, there are many more bits. We assume that n is pretty large. And what I also do here is I display 31 bits per row. Each row has 31 bits exactly. So how do we compress that? Well, the method I'm going to explain is called word-aligned hybrid. And this method that I'm going to explain is actually a blend of 7-bit encoding. We had a video on that. Plus run length encoding. We also had a separate video on that. So this 7 becomes a 31. So it's actually 31-bit encoding plus run length encoding. That is what I'm going to explain in this video. So how does this work? This is the uncompressed bitmap, and that is what we want to compress. And we basically loop over the bitmap, and in each iteration of the loop, we look at the next 31 bits. So to start with, that is what we're looking at currently, and we compress that. So there are two situations we have to differentiate. The first is all bits are set to 0. That happens here in the second row. Or at least one of the bits is set to 1. So that is the situation we're currently in. So what we do is we represent those 31 bits by 32 bits in the compressed output. So here underneath I'm displaying the output, and here each row has 32 bits rather than 31, which means I add another special bit here that is called the signal bit. This green thing here, that's called the signal bit. Just like in 7-bit encoding, I have one signal bit for every 32 bits. So 1 plus 31 gives 32 bits. And as I have in the input some bits that are set to 1, I just take those 31 bits as is, which means I just copy those 31 bits here. That is what is marked in yellow. It's the same stuff. Here the yellow stuff is copied to the output as is. Just in front of that I put this 0. 0 actually means literal, LV literal. In other words, what follows should be taken as is. We need that when decompressing the data. So let's look at the next iteration. So here we have one row of zeros and another row of zeros. So what we do when compressing the data is we consider all the rows until we reach a row that has something set to 1. So here we can take 2 rows at a time. Those 2 rows can be taken at a time, but rather than copying those bits to the output, we do something that is very similar to run length encoding. So again, we put a special signal bit here, and now this signal bit means fill. This is a fill word, And here, the following 31 bits have a different meaning. This part here is a pattern that follows. So in other words, let's write it down here. This is a fill pattern to use. So here the blue number is a number of repetitions, all of the blue stuff. So there's a lot of room for repetitions. So there are repetitions. Okay, so this signals how many times do I repeat this specific pattern. So that is how I compress these long runs of zeros. So let's proceed with the algorithm. So here there's another bit sequence of 31 bits. That's the next row, the fourth row here we are looking at currently. Here some bits are set to 1. So we have to take it as a literal. This is 0, so this is a literal. So we take it as is, just we prefix it with this other bit, this 0, which signals it's a literal. So when decompressing, I can simply detect this. I see that this is literal, so I simply output those 31 bits that are marked yellow here. So let's continue. Here we have a block of 3 rows, all filled up with zeros. So again, I have to write a fill word. So I write this 1 signaling fill word. I write the pattern, that is 0. And then I have to mark the number of repetitions. So that is done here. This is 3 in decimal. So basically what this represents is 3 blocks of 31 0 bits each. That is how I compress it. And so forth. So here's another literal. So I have to write down 0. And then I just take whatever is shown here as is. And so forth, and so forth. That is how I compress data in word-aligned hybrid. So how do you decompress? Well, when decompressing, you do not consider 31-bit chunks, you consider 32-bit chunks. Whatever the file is, whatever the data is, you loop over the data and consider 32-bit chunks at a time. And then you have to inspect the first bit of every word, because you have to detect what you're looking at, the word you're looking at. Is it a literal or is it a fill word? So if it's a literal, it's really easy. You just take the remaining 31 bits as is and copy those bits to the output. If not, so if the first bit, the leftmost bit, this is again, this is what we do. So here the bits are numbered from 1 to 32. We're looking at the leftmost bit here. Is it 0 or is it 1? That is what we're looking at. So in this case here, we take the remaining bits. Those are the remaining bits. We copy them to the output. If this is set to 1, however, then we have to inspect the other special bits here. First, the fill pattern has to be inspected. That is the second bit from the left. This bit here, this is bit 31. That is a pattern. And then everything else is signaling the number of repetitions as explained in the example above. So here the repetitions is the remaining bits, and that tells me what to copy to the output. How many times do I have to copy this 31-bit pattern? Yes, this is a 31-bit pattern. And this pattern can either be just zeros or just ones. That is determined by this fill pattern, which is just a single bit. In the example above, it was just a 0 at all times, but it could also be a 1. So that gives me the pattern, and then this gives me the number of repetitions. How many times do I have to write this 31-bit pattern to the output? That is the basic idea of word-aligned hybrid, which is a blend of k-bit encoding. We could name it k-bit encoding. Previously, this was 7-bit encoding, but basically here the k is set to 31 plus run length encoding. So this method is really a blend of those two algorithms. And there exists some extensions of that. So basically what they do is, you can change the k. So if it's a 64-bit architecture, maybe you want to use 63 bits for alignment reasons. So other things you can do is, so if you look at those situations here, basically you have only few repetitions, and then you have all these zeros that are just wasted, so to say. You could think about extending the pattern, for example. So rather than just having one signal bit, you could extend that to have a higher number of variations. So basically, in that situation, you reduce the number of possible repetitions. So you could also say, okay, just up to here, those are the repetitions in this area, and then you store some other metadata here, maybe a more complicated repetition pattern that's stored here. Rather than just having one bit signaling the pattern to use, you have a more complex pattern. So that is what some of those methods do. There are other tricks you can play. But the basic idea of word-aligned hybrid is what I just explained. If you liked this video, don't forget to hit the like button. Thank you. So if you want to see more database videos, be it in English or in German, take a look at my website datenbankenlernen.de. It has a couple of English and German videos. You can also subscribe to my YouTube channel, Jens did, or you look at our website infosys.uni-saarland.de. See you there!